Morning, everybody. It is very pleasant to come here and share some of the things what we are doing. In fact, we have 3 presentations today, so we'll start today with the PGAS models. So broadly, as many of you know, like we are in a very exciting phase of the Accelerator Era, and if you take a look at like the latest November 2014 rankings, you will see there are 28% of the systems use accelerators, and of course, out of them, 57% of them are using NVIDIA GPUs. And it is increasingly becoming important to actually utilize these kind of accelerators for large-scale systems to obtain the maximum performance. Now, the question is like, once we are trying to use these kind of systems, so where do it fit in terms of the parallel programming models? As many of you might be knowing, the MPI has been the most common programming models, and a lot of work has been going on in the community for GPUs, including our project also, which I'll be talking at more details later at 5 o'clock. But the new thing which is coming in the right-hand side, you will be seeing this Partitioned Global Address Space model. So the whole idea is that these models are being set on top of like distributed memory models, but then it provides flexibility for users to use the global address space. So with that kind of a background, I'll quickly go over the overview of the PGAS models, especially 2 of these, OpenSHMEM and UPC. And then we'll try to explore what are the limitations of using this kind of PGAS models for GPU computing. I'll propose some designs and alternatives, and then show some initial numbers. And then towards the end, I'll try to see what are the challenges to exploit even the GPUDirect RDMA for these kind of programming models. So the PGAS models broadly tries to provide simple shared memory abstractions. It provides very lightweight one-sided communication. It provides flexible synchronization. So there are different approaches the community people are exploring. One is the library-based things like OpenSHMEM or global arrays or Chapel. We'll touch some OpenSHMEM issues here. On the languages side, it also work on UPC, CUDA-aware Fortran, and X10, and I'll try to cover some of the aspects in the UPC. How many of you are familiar with OpenSHMEM? Okay, so some of you, not all. So it is basically the SHMEM implementations. If you go back in the literature, there were a lot of different kinds of solutions out there, like CRAY-SHMEM, SGI-SHMEM, Quadric-SHMEM, HP-SHMEM, G-SHMEM, etc. But what was happening is that all these packages were trying to do more or less a similar kind of things, but with some differences. For example, like if you think the initialization was different between all these, or how do you identify your MyPE, that was also different. So many application codes were not portable across all these systems. So a few years back, there was an effort from the Oak Ridge National Labs to bring together all these kind of different implementations under a single umbrella called OpenSHMEM, so that the community can try to adopt it. And it was based on the SGI-SHMEM, and most of the initial work has been done by the University of Houston. So the way it works, like the OpenSHMEM memory model, if you take a look at it, broadly, let's say we have the different P's or the processing elements, and you define your symmetric data objects which are globally addressable. And they are allocated using a collective like a SHMEM malloc routine. Like the right-hand side, you see, let's say, you try to do it in one P, you initialize, let's say, the variable the B, but that variable B also is locally available. So you should be able to use that on the local reference to get the data from the remote. So the address of a remote object can be calculated based on the info of a local object, and that tries to give you a very nice way of accessing the remote objects. So similarly, if you take a look at the UPC, I don't know how many of you are again familiar with UPC. Okay, some of you. So this has been like a parallel extension to the C standard over the years. Like it was introduced in 1999. After that, like different specifications are coming up. The latest one is the 1.2, which was released in the 2005, and then the version 1.3 is still under draft is available. So there are different kinds of UPC consortiums, academic, government, commercial, etc. Also several UPC compilers are available. So the aim again is to provide high performance with good coding efficiency for irregular applications. So the way the UPC memory model works, again, you have a private space and a global address space. So let's say these are the different threads, and the global space can be accessed by all the threads, but the private space holds all the normal variables can only be accessed by the local threads. So there is a small code example is shown here. You can identify like a shared int A1 threads. That is like a shared variable. So then everybody has the local access, like A1 0 belongs to the thread 0, A1 1 to thread 1, etc. So as these programming models are coming, of course, they are getting a lot of attention towards the exascale computing. And as we know, the systems are becoming more and more complex. So in that way, people are also thinking to come up with hybrid MPI and PGAS together. So the idea is to have MPI across the address space and PGAS within the address space. And MPI is good at moving data between the address space. And then you can use the PGAS models to exploit more locality so that you can combine them together to achieve the best solution. But then the challenge is that how do you really try to write applications to take advantage of this? And in practice, it will be very hard to like rewrite complete applications. It will be harder. So the question people are asking is that, can we do like some application subkernels can you modify? For example, let's say you might have 100,000 lines of code and some subroutines are not scaling. Okay? So then the question is, instead of rewriting the complete applications, can we actually rewrite some of the kernels? Okay, using the PGAS language, if that helps you, then you can combine them together with some kind of a unified runtime so that you get the best benefits of distributed computing model as well as the shared memory model. So in our group, we have been actually working on this aspect for the last several years. If some of you are familiar with this MPI+PGAS, so that actually supports, if you take a look at from the top, it actually tries to provide you all different calls. It can actually provide you support MPI calls, UPC calls, CAF calls, as well as OpenSHMEM calls. And we have a unified MPI+PGAS runtime, and that can run on any of the RDMA-enabled networks like RDMA, InfiniBand, Rocky, or iWarp. And this has been there since 2012. So this actually provides you all flexibility. You can write MPI plus OpenMP program or pure OpenSHMEM program, pure UPC, pure CAF, MPI, OpenMP, any of these combinations. So the idea here is to, if for a given applications you want to choose the best programming model or any combination of the programming models, this framework allows you to experiment with that and then achieve the objective. But this has been there from the host side. This package is there. People have been using it. But now the question is like, how do we bring the advantages and features of GPU to this framework? So now if you take a look at, let's say, think of very simple like the OpenSHMEM. As we saw the PGAS memory models, they don't support the disjoint memory address space. So let's say take an example of the OpenSHMEM. So what you can do is like, let's say we have two PE0 and PE1. We have the host buffer. You do SHMEM malloc. And then you have to do the CUDA mem copy. And then after that, you have to do a SHMEM put memory. But then you need to go through barrier. Okay? So that is the current way you can try to use the OpenSHMEM. But then, of course, once you go through the barrier and then do a CUDA mem copy, this CUDA mem copy and the synchronization actually negates the benefits of this one-sided communication. So even though you can do it now, you will not get a very good performance. So that is the challenge we want to resolve. And you will see similar kind of limitations with UPC. So here what we have done is we have tried to create like a global address space with both host and device memory. So on the top, if you see like the host memory, we can define shared space as well as private space. The similar kind of things we can do in the device memory. So you can have a shared space on the device memory, and we can also have the private space. So then we have actually extended some of these APIs. So for here, for example, like we can have a heap on device or heap on host, the way to indicate the location on the heap, and it can be also similar to dynamic allocated memory in the UPC. So a typical code will look like this. So we have a heap on device, then you have a device buffer with SHMEM malloc, similar kind of things. You can do it on the host, and after that, you should be able to utilize all the calls. So now after the device memory becomes the part of the global address space, so they are now accessible through the standard UPC or OpenSHMEM communication APIs. You can do data movement transparently handled by runtime. It will preserve the one-sided semantics. Now the challenge is how do we bring the performance? Okay, so we resolve it from the semantics layer, and then we want to bring the performance. So here we can do like the standard internode transfers, intra-node transfer using CUDA-aware. Then the question is how do we take advantage of GPUDirect RDMA? So again, the goal is to enable high-performance one-sided communication semantics with the GPU device. So let's take a look at some of the performance numbers here with these kind of designs, how much we can achieve first with the normal designs, and then I'll talk about the GPUDirect RDMA design. So here it shows some numbers. This is like the left-hand side is a small message, and the right-hand side is the large message. And here you will see that this is the standard latency graph for different message size. And here if you just do the naive way, like using the CUDA-mem copy, of course you don't get performance. And here you can, with the selective CUDA registration, here you will see that we can give you around 22% benefit for 4-byte messages. And the large messages, you can get benefits like we have the traditional design in whatever we have in the MPI. We also can try to use here, like the pipeline overlap through the host. So here you will see like for 4 megabytes, we get around 28% benefit. So this was available like in the, we presented this result at the IP+PGAS 13. So now if you take a look at the intra-node, so now you can see that we can also try to take advantage of the IPC. So here we are showing again the latency numbers on the small message and then the large message. The red one is the naive one, and then the green one is the enhanced one, what we are proposing here. So by using this, you will see for small messages, we can deliver you almost 3.4x performance improvement for 4-byte messages, and for 4 megabyte messages, we can improve the latency by a factor of 5. Okay, so those kind of benefits you can see with this new design. So then we try to evaluate it with some application kernel. So here it is trying to show a stencil 2D. We have run it up to 192 GPUs. So the left-hand graph is trying to show we are keeping the problem size per GPU. We are changing from 512 to 8K by 8K. And the right-hand side graph is showing the it's a 4K by 4K problem per GPU, but then we are increasing the number of GPUs. So here we modified the SOC stencil 2D kernel to use the OpenSHMEM for cluster level parallelism. And now you can see like on the right-hand side, the enhanced version actually shows 65% improvements on 192 GPUs with the 4K by 4K problem size. And also like using this OpenSHMEM, we can try to do handle efficiently the non-contiguous transfers. And that actually helps us to get these kind of benefits. So then we also evaluated another kernel, the BFS. So here, again, we extended the SOC BFS kernel to run in a GPU cluster using the level synchronized algorithm and using the enhanced OpenSHMEM. So what we are trying to show here is the total execution time, and the x-axis is the number of GPUs. And here we are running with 1 million vertices for GPU with degree 32. And here we can see like for 96 GPUs, we can actually get an improvement of 12% with the 96 GPUs. And we see a consistent improvement also as we scale from like 24 to 96 GPUs. So then the question is, so this is the standard like without using the GPUDirect. So very recently we have started exploring how we can take advantage of the GPUDirect RDMA. So here it tries to, so these are very fresh numbers kind of things. So what we are trying to share with you. So we try to utilize, this is the GPUDirect RDMA, or what we, in an abbreviation, we call GDR. So this is for small and medium message sizes we are trying to show. So there are 3 graphs here. So the top left right corner is the small message SHMEM put operation. So that is a common put operation in the OpenSHMEM, and we are trying to do device to device. So that means from the device buffer, the GPU buffer, we are trying to use the SHMEM put call to the remote GPU. So here you can see like the standard host pipeline, if you take the data through the host pipeline, it is almost like a 20 microsecond. But if you use the GPUDirect RDMA, then we substantially reduce it. And here we see like for 4 byte, we can actually try to transfer that in 3.13 microsecond, this OpenSHMEM put call. And that gives around like a factor of 6.6 improvement here. And if you see also the blue line there, it remains very flat. And that is very good for the GPUDirect RDMA, like up to 4 kilobytes. It doesn't change that much. We are able to achieve this transfer operation with 4.7 microseconds. So then the left hand, the bottom graph, here we are trying to do the SHMEM get operation. The top one was a SHMEM put. This is a SHMEM get. So that means we do from the remote GPU buffer to bring it here. So similar kind of trends we can see compared to the host pipeline. If we go through the GPUDirect RDMA, we see like a factor of 9 improvement here. And then the right-hand side, the top graph, which is showing the large message SHMEM. And of course, here we don't have significant benefit because here we go through the host pipeline because GPUDirect RDMA is not good for large messages. So in our MPI design also, we take it through the host and then push it. The same design here we are using, so you don't see the benefits there. So then this is the next one is the intra-node. So here what we see is like the left-hand graph is trying to show the small message SHMEM put device to host. And here we see the GDR can be used again for small and medium message sizes. We can use IPC for large messages to avoid the PCI bottlenecks. And then we have the hybrid design, which tries to combine both. And here, if you see the left-hand graph, for 4 bytes, we can do the D to H, the device to host, in 2.42 microseconds. And that is like a 2.6 improvement compared to the red line, which is the IPC. So we can take advantage of the GDR to in fact to do better than the IPC. And for the right-hand side, we have the gate operation, and so there we see around like a 3.6 x improvement for the gate operations. And similar results also we have seen it for all other operations like D2D, S2D, and D2H. So I'm not including these numbers here. So then we tried to do the similar kind of evaluations using stencil 3D, what I showed earlier for the normal like the host-based thing. So here we have what we are trying to show again across the number of GPU nodes from 8 to 64. The input size is like 2K by 2K by 2K. And this the numbers were taken on Wilkes system, that is the University of Cambridge system. They have the largest GPU cluster. This was taken with Intel Ivy Breeze, NVIDIA Tesla K20s, and Mellanox Connect IB. So here if you see, again, like across the number of GPUs, you will see we get around like 20% to 19% improvement on the 32 and 64 GPU nodes. So these are the kind of benefits. Now what you can see, trying to bring multiple aspects. Like the first is trying to extend the OpenSHMEM model, how we can take advantage of the GPU. And then on top of that, we try to use all these OpenSHMEM and IPC, all our mechanisms to put together so that in a very practical manner, if you want to use OpenSHMEM on the GPU-based cluster, you should be able to evaluate it or get the best performance and scalability. So this paper is under review. What we are trying to show you here is like a preview of the results. So to conclude here, what I presented that the PGAS models, whatever are upcoming, they try to provide you the lightweight synchronization and one-sided communication semantics, and they try to provide you the low overhead synchronization that is good for GPU architecture, but the way the current state of the art lies, you cannot really take advantage of the GPUs in a very efficient manner. And I presented some of the extensions that can be done to the PGAS, especially for the OpenSHMEM, to efficiently support the CUDA-aware PGAS models. So we have heard about CUDA-aware MPI. We actually introduced many years back, and that is getting a lot of attention in the community. A lot of MPI stacks have gone to the CUDA-aware MPI. Similar kind of things here we are trying to do CUDA-aware PGAS. So that is the broad goal of this work. And we also see that we can have highly efficient GDR-based designs for the OpenSHMEM, and our next plan is to actually exploit the similar kind of GDR-based designs for UPC. So with this, let me conclude here. And of course, our plans are to take these designs into the MPI+X, which I introduced earlier, which tries to provide you the complete support for all the different programming models. Currently, they can run on the host, but we want to bring the GPUDirect RDMA into that support so that you will have from the end user perspective, a complete solution. So with this, I'll conclude here. As I indicated, we have 2 additional talks coming up. The 2 o'clock will present something very new, which we have done recently. A lot of people have been asking for. How do you combine the InfiniBand hardware multicast support with GPUDirect RDMA? Okay, so these 2 features come from different technologies. The GPUDirect RDMA allows very fast communication from GPU to GPU, but that is only point-to-point. But on the other hand, InfiniBand provides this hardware multicast where you can do very fast multicast to a lot of nodes. So the question is, can they be combined? And that's what we'll see it at 2 o'clock. And then at the 5 o'clock, we'll go into much more details on our MPI+2 GPU project. How do you take advantage of all the latest things there? So with this, let me close here. And if there are very quick questions, I'll be happy to answer. There are two members of my team sitting here. Khaled, the senior research associate, and Akhe is a PhD student. So they are here throughout the conference. So we can handle some questions now or throughout the day or later on. They will be happy to answer this. So thank you.